To begin to derive any type of equations relating to fluids, we first need to understand what forces are acting on the fluids themselves. We will begin by working with static, or not moving fluids. Imagine a glass of water. Now imagine there's a tiny amount of water that we want to focus on. We can consider this to be our system. Now let's analyze the forces that are acting on this small fluid element. There are two types of forces that act on this fluid element: body forces and surface forces. Body forces act on the entire volume of the system. You can think of them as forces that simply appear because of the object's existence. A common body force that we will be using is gravity. If a system has a volume and a mass, gravity will always be present. Other examples of body forces are electric forces and magnetic forces, but those are not as relevant for this class. Now, surface forces. As you can probably tell from their name, they act on the surface of a system. So it's other stuff acting on our system of interest. They appear when the system comes in contact with their surroundings, which is why they're also called contact forces. When we consider our system, the only body force that we really care about is gravity. If you remember the equation for gravitational force, it's force equals mass times gravity. Since gravity only has one component in the y direction, the body forces for the x and the z components will equal to 0. This implies that the body force for gravity is only present in the y direction. Now let's move on to surface forces. Let's imagine our system as a tiny cube. The dimensions of this cube would be dx, dy, and dz. Assuming we know nothing about the pressure, we can assume it changes based on the location that we're at in the fluid. We can write this as a different pressure force on each of the sides of the cube, starting with the x component, then the y component, and then the z component. We will write P plus dP to signify a change in pressure on the opposite side of the cube. The drawing is starting to look complicated, so let's remove everything except for the x component pressures. We know the equation for pressure force is force equals pressure times area. The derivative of this will be dF equals P times dA. In this case, dA will be dy times dz. Next, we can calculate the total change in the surface force in the x component using this next equation. Simplifying down, we obtain dF equals negative dP times dy times dz. We can divide by dx to get the next equation. In this case, F equals ma is going to be equal to 0, because the fluid is stationary and acceleration is also equal to 0. We can now see that dpx dx equals 0. This means that the pressure component of x does not change as x is changed. This applies to the x, y, and z coordinates. This will mean that the surface forces on the system are equal on all sides. This is not to say that they are equal to 0, but they are equal to each other when acting on opposite surfaces of the system. So at the end of the day, if we wanted to sum the total forces acting on the system, we would sum the body forces and the surface forces. We know that the change of the total forces in the x direction is equal to 0, since the fluid is stationary. This means that the sum of the body forces and the surface forces is equal to 0. Expanding out the equation, we can see that since the body forces are 0, so are the surface forces. If we do the same type of analysis for forces in the y direction, we have the same kind of setup. The total change in the forces is equal to the body forces plus the surface forces combined, which equals to 0 in total. However, this time the change in the body forces in the y direction is equal to mg. Taking that relationship, we have dP times A plus mg equals 0. In this case, A is equal to dx times dz. We can also express mass as density times volume. If we divide everything by dx times dy times dc, otherwise known as volume, we get the following expression: dP dy plus rho g equals 0. From this we obtain the final expression dP dy equals negative rho g. For the z direction, we repeat the calculations for the x direction. Since the sum of forces is equal to the body and the surface forces, which in total is equal to 0, we do not obtain a relationship between pressure and change in Z. Just to recap, all of this was done to understand if the pressure changes when moving around in the x, y, or z directions in a stationary fluid. As can be seen from our previous derivations, the pressure does not change when moved in the x or the z directions. The pressure changes with change in y, under the equation negative rho times g. This means that when in a stationary fluid, the pressure does not change when staying at the same depth. However, when depth is increased, pressure also increases. By integrating that derivative, we can obtain the commonly known expression for pressure at a certain depth. P of h equals rho gh, where h is the distance from the surface. This is an equation that will be used a lot in this class, so try to remember it. It's time to make an important distinction. If you look at the formula we just derived, plugging 0 in for h will lead to a pressure of 0 at the surface of the water. This doesn't make sense because a pressure of 0 would indicate a vacuum. So anyone at the surface level of water would be looking like Arnold in the Magic School Bus when he takes off his spacesuit in space. To understand this, we need to learn about something called gauge and absolute pressure. These are two different ways to measure pressure. Gauge pressure is a value for pressure which is obtained by measuring a pressure difference from a reference. This reference is typically atmospheric pressure, which is 1 atmosphere. Absolute pressure, on the other hand, is a value measured as the pressure difference from vacuum. Our equation, P equals rho gh, uses gauge pressure. So if you're looking for the absolute pressure, add 1 atmosphere to that value. As a final review question, you dive into the deep end of a pool. What is the absolute pressure 3 meters underwater if we assume that the density of water is 1,000 kilograms per meter cubed and gravity is 9.81 meters per second squared? I'll give you a few seconds to think about how to set it up, or pause the video and try solving on your own. To calculate the absolute pressure, we add 1 atmosphere to the pressure equation, which is rho gh. Remember that 1 atmosphere converts into kilopascals, which is going to be the units that we are using. And then the final answer would be 130.755 kilopascals. Thanks for watching this video, and I'll see you again next time.